All right, well, hey, welcome to Math 204 Differential Equations. My name is Bruce Armbrust. I teach math and physics here at the college, and I am super excited to show you guys differential equations and kind of lead you through this class. Um, Before we get to what differential equations is, let me just talk a little bit about my expectations of y'all and what you're going to need to do for this class. Luckily, I know most of you. I know almost all of you, and you guys all know me, so there shouldn't be a huge learning curve there. But just to make sure that we're all on the same page, just a couple of things. First of all, in terms of attendance, coming to class, not coming to class, that's totally on you. I don't really care. You're here or you're not here. I'm going to proceed regardless. Just make sure if you're not here to catch up on things by watching the recordings of these that are up on my YouTube channel or talking to your classmates or whatnot. So come to class, don't come to class. I don't really care. In terms of Zoom protocol, number one, please stay muted unless you're actually talking with questions and comments and stuff like that, because sometimes the background noise can be distracting. Also, when this records, it goes to the speaker view. And so if there's some background noise, it sometimes will shift the view away from what I want you guys to see to that person's screen. So just do me a favor and keep them muted. I don't think that's going to be an issue with you guys. In terms of cameras on or off, obviously I prefer cameras on. I know that most of you prefer cameras off. It just makes it a little bit more exciting for me if I'm not just staring at names, but I totally understand, and it is your prerogative. I also know that you guys in previous classes, you tend to be pretty active, at least in communicating with me, either talking or through chat. So as long as you're communicating with me, that's good. But again, I prefer video, but it doesn't need to be on. All right, so let me go ahead and share my screen. I want to share the syllabus here, and let's talk a little bit about what you're going to need to do for this class. All right, so in terms of contacting me, best way to get a hold of me is by email. I did kind of blot it out here because I don't want it on the YouTube. But you've got access to this on your Canvas shell. Most of you already know how to get a hold of me, but email is sort of the way that we need to do things. And I will get back to you hopefully within, not hopefully, within 24 hours, except for possibly on weekends or holidays, because I also have a life that goes beyond differential equations. And also realize that it may not be instantaneous response because there are certain hours of the day when I am not available, right? Like right now, if I got a text from or an email from one of my, say, trig students, well, they're going to have to wait till I'm done with class before I can address it. So obviously, I'll get back to you. It just may not be right away. In terms of how we're doing class, this is going to be in this, what we call the EVE, the Enhanced Virtual Education setting, where we're in the Zoom classroom. So we'll meet in here just like on class, like on campus, from 1 to 2:40 on Monday, Wednesday, and Friday. And yeah, I try to do my best to treat it just as if we were on campus. But as I said before, I do record these things and put them up on YouTube. I do have a channel. Just do a search on Bruce Armbrust LTCC lecture series, and you'll find them. And I do separate them by classes, by the different courses. So you can always go and look for the ones that are Math 204. Now, just so you guys know, Math 204, I also did last year in EVE, and so I did put up videos. So if you're to go over to my YouTube channel now, you're going to see a whole string of Math 204. Those are from last year. So if you want a little preview of things to come, you can definitely go there and check them out. I do put the dates on them, so make sure you're looking for the ones that say 2021. And those will be for this specific class. But I think they also put them up in order in terms of when they were uploaded. So you should be able to see them, see the right ones. All right, so office hours. I've decided I've changed the name of office hours. I'm calling them student hours because I think that's more appropriate. Student hours, times for me to be accessible to my students, to you guys. I'm going to be doing these again on Zoom, and it's actually the same office hour link as before. So if you guys have that from previous classes with me, you can still use the same one. If not, it's on the syllabus. It's in the class, in the Canvas shell. But the times that I'm going to be available, you'll see that they are a whole smattering of times, Monday through Thursday. I don't actually have any on Friday, just because I tend to have some meetings on Friday that make it hard for me to dance around with office hours. But you guys should also know, though, that I'm very happy to meet with you at other times. So if you look at those times and go, well, crap, I work at all those times, send me a message. I'll be more than happy to find other times to work with you. We'll just work around our schedules. So realize that that's a time to come and ask me questions about what's going on in math if you're having trouble with the topics, but also we can talk about other things. Like I know a lot of you are planning on transferring now. If you have questions about things potentially transferring or majors or things like that, I'm more than happy to talk about that stuff as well, including technological issues. Or if you just want to shoot the shit and talk about how horrible your baseball team is, I'll be more than happy to commiserate, right? So anyway, those are times you can definitely find me, and I'll be happy to work with you. If for any reason they change over the quarter, I mean, I don't think there'll be a wholesale change. I think there might be a couple times where maybe, oh no, my Tuesday one has to get canceled or whatever. I'll be sure to let you guys know through Canvas, and we can make alternative plans. All right, so the textbook that we're using is actually an online textbook, a open resource. So that means to you guys, no money, costs you no dollars for this book. I gave you the link here, and I'll go ahead and just pull it out. I got the PDF of it up here. Let's actually go to the front here. There we go. So it's Elementary Differential Equations by William F. Trench. All right, so it's a standard differential equations book, but this is the one that we're going to be using. All right, so no cost to you.
Do you like it?
Do I like it? It's fine. I don't know that I've met a differential equations book that I really like, because they all are they all have their own quirks to them. But this is a perfectly fine one, and yeah, I like it enough to use it. It's not the only free one out there, but it's definitely a quality one. So I don't know if that was a good enough answer to your do I like it or not. We kind of danced around it, but yeah, it's a pretty good book. Okay, so what are we going to be talking about? Right, well, we're going to be talking about solving ordinary differential equations. That's the name of the class, differential equation. And just like calculus, like think back to calculus when you learned about, say, derivatives or integrals. You were introduced to them, and then you just learned all the different processes, and then you did applications. Well, it's the same model here. Differential equations, I'm going to introduce you to them. What are they? How do they work? Then we'll learn how to solve them. And the how to solve them, it's as varied as how to integrate or how to differentiate, right? Like think about, I like to go back to the integration one, because integration techniques, there were way more. Like if you go to derivatives, really there was like product rule, quotient rule, chain rule, right? And even quotient rule you didn't need if you just thought of it as product rule and chain rule, right? So there weren't a lot of things, but like with integration, oh my God, we had U substitution, trig substitution, integration by parts, partial fractions, right? Like just the list goes on and on and on. Well, differential equations is going to be kind of the same way. We're going to learn how, all the different techniques for differential equations, which like integrals is going to be all about looking at the form and recognizing the form, saying what method it's pushing you towards, right? So we're going to learn how to do them, and then we're going to apply them, because any good math class should show you why you care about this. And differential equations is no different. So kind of the same story. as everything that you've done now in college with math. It's a different topic. So you'll see in here, we got things like exact, separable, linear, integrating factors, undetermined coefficients, variation parameters, Laplace transform, series solutions, blah, blah, blah. All right, those are just all the different methods that we're going to learn. All right. So in terms of grade, because this is actually what you really care about, the student learning outcomes, that's what you're going to learn. Course grade, classic 90, 80, 70, 60 thing. But as you're starting to notice, the portions of what go into your final grade are getting smaller and smaller, or the things that are in there are getting more and more valuable. This is kind of what happens as you go further on in college classes. Just wait until you get to the class where your grade is your final. That happens, right? Or it's just the midterm and the final or whatever. Well, here I still have homework. We're going to have homework sets. That's going to be worth a quarter of your grade. There are going to be 2 regular exams. Those are both worth 20% of the grade, and then a final exam that's worth 35% of your grade. Okay, so that's kind of the breakdown. And you can always see what your score is on Canvas. The gradebook will show it to you, and it will get updated as things get graded. But here's where this is going to be a little bit different than calculus, and maybe more similar to linear algebra, because I'm going to guess in linear you didn't use something like MyOpenMath. This is going to be kind of old school, do the homework problems, write them out, and upload them kind of deal. All right, so what we'll see, and I'll show this to you in a second, is that each of the sections, I give you a list of homework questions. They're not very long. You'll see that they're really just a handful from each section. But what you're going to do is you're going to work them out, right, do your answers, and then you're going to upload that file onto Canvas. I strongly prefer PDF format. That makes it a lot easier to grade, a lot easier to read, a lot easier to deal with. But if you don't have an easy way of doing that, like an app on your phone or something that's a PDF format maker, photos are fine, right? Just make sure that they're legible. Sometimes that's an issue with photos. When you use your camera to take a picture of it, your phone to take a picture, is it might be a little out of focus. Some of them might be cut out. It's in your best interest to make it legible, right? The more legible it is for me, the easier it's going to be for me to grade, give you comments, and the happier I'm going to be. I'm not going to lie, right? So, but go ahead and upload those through Canvas. And I'm going to give you a similar deal as you've had before. So we'll just kind of highlight this one at the end. If you do all the homework and get a score of at least 50% on each assignment, then you will not need to take the final exam. Meaning at that point, if you're happy with your grade, we can call it good. All right. So do your homework, and there's a pretty significant carrot for doing it. All right. So then the exams, they are going to be take home open book, right? You've got all your notes, everything. I don't use Proctorio. I find that that's a bigger headache than it's worth. And honestly, a lot of the stuff for this exam is not the kind of thing that you can just type into, Symbol Lab and all that. I mean, obviously there are some things, but a lot of it is going to be more, you need to show me what you're doing. And those resources don't do that. So, but anyway, they are going to be take home open book. And like in my previous classes, most of you are familiar with how I'll do this. It's going to be on a class day, just like normal. So they're going to open up at 1 o'clock, and you'll have until 3:30 to get them uploaded. So basically think of it as it's the 2-hour exam and an extra half hour to deal with, getting it uploaded and dealing with all that sort of stuff. All right. Okay. And the final exam, same kind of deal. It's a slightly different time schedule, and I'll show that to you in a minute. If you need alternative testing times, like if you go, oh man, it would really be beneficial if I could start it at 12:30 instead of 1 because I got to get to work, or if you're a DRC student and you have extra time accommodations or whatever, let me know. We can work on that. try to find a time that's convenient. We're going to try to do it as much as possible during class time. All right, so the registration info is just there for your reference. Those are the drop dates, although nobody's going to drop this class. We're all going to make it through and call it good. How to succeed in a math class. You already know what you need to do, but I do want to highlight here number 4. When I say here, make use of available tutors in my student hours. Unfortunately for you guys, tutors are not readily available. In fact, I mean, I don't even know exactly who all the different tutors are that are currently employed, but like if Chad is still there, he knows it a bit. Yeah, so I don't even know who in there knows differential equations. So that's a little bit tougher, but I do know that there are places online where you can get some tutoring, and I think the college even has some sort of tutoring program access kind of thing. But for sure, you've got me. And I'm going to volunteer Larry as well. He doesn't know that I'm doing this, but I know he'd be fine with it. Obviously, Larry knows differential equations and can help you out as well. So if you're not getting what you need from me, don't hesitate to reach out to him. But come and talk to me. I want to help you out, and don't let pride get in the way. You also know that I'm not going to judge you for any gaps in your knowledge. I'm not that guy. I might silently judge you. No, I won't judge you. You know this. So, but come to me if you need help, because that's my job. That's why I'm here, is to help you learn differential equations. Again, DRC students, if you work with the DRC, please contact them and contact me. Let me know what kind of accommodations I can do to help you out. I put here the library and learning services link, Cranium Cafe. You guys know that that's where you can get things like textbooks, not like that matters here, but you can get like Chromebooks and stuff to borrow. Some really good news. This is kind of new since I wrote the syllabus. The campus is starting to open up a bit, including the library. Like, for example, you can reserve time in the study rooms and all that. So if you want to get out of the house, find a quiet place to study, you can now start doing that on campus. There still are protocols with things like masks and getting clearance using the Campus Clear app and all that. But I just want to put that out there. It might be worth going to the college website and digging around and just sort of seeing if that's what you want and if you're willing to go through the steps necessary to do that. All right, so that's kind of exciting. We're starting to get back to normal, and rumor has it we're going to actually have a live graduation. At least they're planning on that, which I know affects some of you guys. You are the ones that are kind of ending, and hopefully I will see you there. All right, anyway, and then lastly, academic dishonesty. Guys, just don't cheat, right? Like, come on, let's be grown-ups about this. Don't use other resources. Show me what you know. Yeah, so don't cheat. Okay, so then class schedule. You'll notice that we pretty much just go in order. So we're going to start in chapter 1, go to chapter 2, and then jump into chapters 4, 5, 6, 7, 8, 9, and 10. All right, so kind of nice. We're just going to kind of follow it in order. You'll notice that I do have the exam dates on here on the schedule. So those will be the days of the exams. We might adjust them, or what's on them. I would prefer not adjusting those dates, but you guys know that I'm happy to do that if things happen and whatever. The one other thing you should know is that May 31st, the last Monday of May, that is Memorial Day. So we will not have class. Again, if we were on campus, we wouldn't be meeting. So in this world, we're not meeting either. So on that day, go enjoy a hike, go enjoy the beach, drink some really high quality root beer, whatever it is you do to celebrate Memorial Day. I mean, hell, if you want to do differential equations, you go right ahead. I'm just not going to join you. Right? I know I'm going to be at a baseball game. The Reno Aces have a game that day, so I will definitely be there. Anyway, so just realized we don't have class that day. And then lastly, the final exam We are scheduled for June 23rd, which is the Wednesday of finals week. But the final time, it actually starts at noon, not at 1, because you know our final exam schedule is just slightly off. But you're going to have, it's from noon to 3. I will definitely remind you guys as we get closer. Some of you probably won't even end up taking it because of the fact that you'll do all the homework and you'll be happy with your grades, but we'll deal with that when we get there. All right, so there's the syllabus. Like I said, I think you pretty much know what to expect. So let me just hop over real quick in Canvas, show you a couple things. So this Canvas shell is pretty bare. For this class, there's not really a lot for me to throw up on there, but I do have links to our classroom, my office hours, student hours. So you click on those, it will take you through the, pull up your Zoom and everything. You can go to the syllabus here, and then I've got the book also as a link. My recommendation actually, when you go to that book, is download it as a PDF. I just downloaded it onto my computer as a PDF. That way I always have it. It's a little bit faster, pulls up faster as a PDF than waiting for all of that incredibly large amount of data to come across the, interwebs. But anyway, all that stuff is there. And then of course, if you go to assignments, that's where you'll see all the different assignments for this class. So we got there's the homeworks. You'll notice that I only have homeworks through 9.4. To be honest, I didn't get to making ones for chapter 10 yet, but we've got a couple of months till that needs to happen. But you've got all the homeworks through chapter 9 already up and ready with their respective due dates. There are a couple I still have to change. There's one I still have to change because they're due Monday night at midnight, right? And that one for some reason says 5 p.m. and not midnight, so I gotta fix that. Anyway, but then here are the exams and the final exam, right? So when you click on one of these, let me just show you what, say, section 1.2 looks like. So you'll see I have problems here, 1, 2B, 2F, 3B, 3C, and so on. So those correspond to those questions from that section. Let me pop back over to the book just so I can show you what I mean. So let's go to 1, 2. Cruise down here to the end. All right, so here are exercises 1.2. So again, if you go back and you look, for example, I wanted 1, 2B, 2F. So you're going to do all of problem 1. But then in problem 2, you're just going to do B and F and so on down the line, right? So again, not super long, but it's enough for you to get some practice. But like you notice how it says here, submitting a file upload, right? You're going to do your work, take a picture, scan it, whatever, and pop it up. Okay, so I think other than that, you guys are pretty comfortable with the whole Canvas deal and how everything works. But that's kind of what I'm expecting out of you guys. So at this point, any questions? We all good? I do not know Larry's office hours, but I'll tell you what, I will send him, I'll send him an email and I'll ask him if he's willing to share his Zoom office room and his office hours to you guys. And then if he says yes, I will, I'll post that somewhere on the Canvas shell so you guys can have that. But that's a good question, Ralph. I just don't happen to know what they are. I actually haven't talked to Larry in, I can't tell you how long, which is really weird because normally he's like, 4 feet away from me in the office. So I've only been on campus like 6 times in this year, which is also really weird. So, and yet it seems like every time I'm there, I see Victor. In fact, I just saw him, what was that, like on Wednesday? I think I came, no, Thursday, and ran into Victor in the hallway. So, all right, any other questions? Or are we ready to talk a little bit about differential equations? You're good? Okay, I'm going to pause the recording just for a second because I need to get my phone up on the whiteboard and I don't want to waste everybody's time. All right, so differential equations. Seems like a easy enough title for a class, but we should probably talk about what it is, what it means, what we're going to be doing. Okay, so first of all, let's just look at the name. And you guys by now know exactly how mathematicians name things. They're exactly what they say they are, right? So differential equations they are equations, duh, with derivatives. Differential, duh. Okay, so differential equations, they're exactly what they sound like. They're equations that have differentials, that have derivatives. All right, so there are lots of examples of these, lots and lots and lots. But let me just show you some. These are things that you actually, some of them you've actually seen. All right, so examples of places where you find them. Just good old integrals. Remember back in the day when you were asked to integrate something, right? So for example, we just said, let's integrate e to the x sine x dx. And looking at that, you might go, well, I don't see an equation. There's no equation, and there's no derivative in it. But we could rewrite that as this, right? What if I had written y prime equals e to the x sine x? How many times did you see something like that in calculus, right? Tons. And if we actually wanted to find out what y was, we integrated. So in this form, you can definitely see the derivative in the equation, right? So here's an equation with differential. So y prime equals e to the x sine x. It's a differential equation. Another place you saw this was stuff with like, say, exponential growth. So you would have seen this in Math 106 in second quarter calculus. And that's the good old like y prime equals k times y. Hopefully you kind of remember that. But there's another differential equation, right? It's an equation with a derivative. Well, I could keep making this list like with all kinds of things that you've seen before. How about this one? Y prime equals ky times L minus y. Anybody recognize that? I'm just curious. And remember, it's always okay to say no. But anyone recognize where that was seen back in the day in calculus? Not temperature, Ralph, but that's actually the next one I'm going to show you, Newton's law of cooling.
Population.
This was a population thing, yeah. Anybody remember what that L did? Yeah, so Ralph just put there as a cap. It was a limit. It was a limiting value. We call it a carrying capacity. So like if you wanted to talk about, you know, number of bacteria in a petri dish, obviously you can't grow exponentially, but it's got to level off. All right, well, that led to a differential equation, right? So something like that, but you can see it. There's a derivative in our equals. So Ralph mentioned temperature. This was like Newton's law of cooling. It looks a lot like that, where we get T prime, so that's our temperature, is K times, say, TA minus T. So that TA is the ambient, the environmental temperature. So I'm not surprised that Ralph thought temperature with that other one, because you look at the form that's pretty similar, right? So that was Newton's law of cooling. I mean, all kinds of stuff. Here's kind of a cool one we could do. Think about air resistance. You remember air resistance, the thing that we always ignored in physics because it makes the math too hard. Well, guess what? We're going to learn how we can deal with the math to handle air resistance. So check this out. Think about air resistance. You've got an object that's falling, right? So it's falling in this direction. And think about the forces that are acting on it. You got gravity, right? Gravity's trying to pull it down. But you also have air resistance, and air resistance is pushing upwards, right? It's pulling against this thing. So we're going to have a couple of forces. We've got gravity and we've got air resistance. Well, let me show you where we're going to get a differential equation here. So what we're going to do first is we're going to say that the air resistance depends on how fast objects fall. And that should make sense, right? If an object isn't falling very quickly, there's not a lot of air resistance, but if it's moving fast, there is a lot of air resistance. Think about this. Next time you're in a car, stick your hand out the window, right? Put it like this. I remember as a kid doing this all the time, right? But think about it, when you're going slow, you don't feel a lot getting pushed back. But if you're going fast, you really feel it getting pushed back because the greater velocity means more air resistance. So if we say that air resistance is, say, proportional to speed, check out how we can create a differential equation. So we're just going to start with our force. The force acting on this thing is gravity minus the air resistance. Okay, so gravity, that's just good old mg. But the air resistance, we're going to say that it's proportional to velocity. And then, of course, from Newton's second law, force is equal to mass times acceleration, right? So this is the kind of thing that you would have built in physics using your, good old force diagram. And you still may not see the differential equation, but let me make you see it. I want you to think about acceleration compared to velocity. How do you get acceleration from velocity?
Take the derivative.
Okay, you take the derivative. So this A, it's actually just V prime. So if we change that, we now have mv prime equals mg minus kv. And there's your differential equation. An equation with the derivative. All this other stuff, m, g, and k, those are all constants, right? M is the mass of the object. G is the gravitational attraction wherever body we're on. K, that's going to depend on the medium that you're falling through, right? Like you drop a baseball through air versus baseball through water, there's going to be a different drag factor. That's what that K comes from. But those are all constant. So the thing that's changing is your V. And we've got a differential equation. Okay, so they are literally everywhere. There are so many applications of differential equations that it's mind-boggling, but we're going to see a bunch of them. But this is all it means. Differential equation is an equation with a derivative in it. Now, all the ones I've shown you so far have just good old regular derivatives, but you could also have partial derivatives. Like there's nothing to say that you couldn't have a differential equation that's like dx dt is equal to x cosine of 3t or something like that, right? So whether you've got a partial derivative, a regular derivative, as long as there's a derivative, it's a differential equation. But you're not restricted to just a first derivative. You could also have things like this. Let's say we had y double prime minus 2y prime plus y equals e to the x. this is still a differential equation. It's an equation with derivatives in it. It's just this time, not only does it have a derivative, but it's got a second derivative. Okay, you have a third derivative, you got a 100th derivative, and it's still a differential equation. All right, so that's all they are. Well, obviously, if we're going to try to solve these things, and I mentioned that a lot of it's going to come down to what type it is or how, what kind of format it's got. We should probably start classifying these things. All right, so in terms of differential equations, we start by splitting them into two big groups. All right, so all differential equations can be split into two types. There are the ones that we call ordinary, and those that we call partial. And of course, because we're mathematicians, we call these ODEs. And we call these other ones PDEs. Ordinary differential equation, partial differential equation. All right, well, this is exactly what they sound like. The partials, those are the ones that have partial derivatives in them. So like this guy that's in the kind of the reddish brown, that's a PDE. Ordinary differential equations have regular old ordinary derivatives, like these guys. Okay, so we have ordinary and we have partial. This class, Mat204, we're going to be looking at only ordinary. Okay, so we're not going to worry about the partials at all. Doesn't mean they don't matter. Doesn't mean they don't have solution. Just means that you're going to learn that in another class. In fact, you'll see, like, if you go to a four-year place, like let's say you go look at Berkeley's math catalog, they will have a class called ODEs and they'll have a class called PDEs. In fact, they might even have multiple classes that are ordinary differential equations and multiple that are partial. So it's just way too much for us to do. So we're going to start just like, we're going to start in the shallow end of the pool. We're going to start with the ordinary. These are the easiest to deal with. They're also they show up frequently. There are a lot of good applications of it. Okay, so we got ordinary. Now, these ordinary differential equations, they also can be split into two types. We have linear and we have nonlinear. We will look at both. We will look at both, at least some of each. But in terms of linear versus nonlinear, the linear, these are such that you don't have powers of y. You don't have derivatives times second derivatives, things like that, right? These are nice. They're nice and easy. But basically, again, so there's like no y squared, no y prime times y, etc. You don't have y inside of sines, right? Things like that. So basically, it's going to be linear, like you think of linear. When you think of a linear equation, you have to change it's not x's now, it's y's. But with linear equations with x's, it's just x times constants. Same thing here. It's just y's times constants, y primes times constants, y double primes times constants, and so on. Okay, so you got linear and you got non-linear. So in our journey this quarter, we'll tackle both of these, but we're going to stay in the ODE world. All right, now another thing that's going to be important that we're going to need when we classify so we can figure out what to do is what we call the order. Okay, so the order of a differential equation. This is going to be the highest order derivative in the equation. Okay, so you're going to look at your differential equation and you're going to see what is the biggest derivative. And so that's the order. So for example, here's a first order, would be something like the good old exponent, the one that led to exponential growth. So y prime equals k times y. Here's an example of a second order. Would be something like y double prime equals y. Right, where the second derivative is equal to y. So now you look at this one, it's got a second order. And so on and so forth. So like, how about this one? If we had, say, fourth order, y to the fourth minus 3y double prime plus 2y equals e to the x, right? This one would be fourth order. It's got a second derivative. It's also got a fourth derivative, but the fourth derivative is the highest, so that's fourth. All right, so makes sense? So one of the first things we're going to do when we're solving one of these things is we're going to look and see what order is it. Because what order it is going to tell you what to do. All right, we have different techniques depending on what order differential equations we have. Okay. So as we proceed, we're going to start with first order. We're going to talk a lot about how do we solve first order differential equations. Then we're going to go to second order. Then we're going to go to higher order and so on. Okay. All right, so a lot of it is classifying them, looking at the differential equation and figuring out what kind it is. So then you know what technique to use. All right, cool. So probably the next thing we should talk about, now we're talking about what they are, is well, what does it mean to have a solution? Okay, so exactly what is that? All right, so what's a quote unquote solution to the differential equation? Like, how do you know what you're when you're done, or what is it that we're looking for? Right, like you think about it with math, there's so many different things that we do that sometimes it's hard for us to know when we're done, right? Well, with differential equations, what are we doing? Well, we're trying to solve the equation, just like any other equation. But now what the solution is, this is going to be a function that satisfies the differential equation. So for example, like let's look at this one, this second order where we have y double prime is equal to y. What we're looking for is a function that when we differentiate it twice, get second derivative, we actually get what we started with.
E to the x.
Okay, how about e to the x? That's a great example. That would be a solution to this differential equation. Is it the only one?
Maybe, maybe not.
Maybe not, right? And that actually gets to be the question, right? Is that, okay, yeah, so like in that example, you found one, well, e to the x, y equals e to the x. Is it the only one? And Ralph just chimed in, no, it actually is not the only one. You could take a scalar multiple of e to the x, right? What about y equals 2 e to the x? Well, its derivative is 2 e to the x, and so its second derivative is 2e to the x. So you can take a scalar and multiply of it, but how about this? What about e to the minus x? That's fundamentally a different kind of function, right? E to the x versus e to the minus x. Well, e to the minus x, if you differentiate it twice, you get back to e to the minus x, right? So that's really the goal with these, is trying to figure out a function whose derivative or second derivative or whatever, when we plug them in, gives us truth. Like this fourth order, it'd be a little bit more complicated. You'd have to try to think of a function whose fourth derivative plus 2 of the original function, but then removing 3 of the second derivative leaves you e to the x. Okay, that one might be a little bit hard just to think up an answer to, but I promise you, let's see, for this one, I think by May, you'll know how to do that. You'll know how to actually find the solutions to this. Okay, but that's what it means when we say solve one of these things, is actually finding the function that when we plug it in does give us truth. So for example, let's look at this guy. Let's say we've got a differential equation that's y prime plus 3y equals 6x plus 5. And what we're going to do, we're going to confirm that y equals ce to the minus 3x plus 2x plus 1 is a solution. Okay, now where this came from, no, don't worry yourselves about that. Not yet. We'll get there. But just for right now, let's actually confirm that this actually works. So here's what it means. We need to be able to plug this in to this equation and see that we get truth. So I need its derivative. So let's just get that real quick. So y prime is going to be minus 3c e to the minus 3x plus 2. So I'm going to plug that into the differential equation. So I'm going to take my y prime. I'm going to add to that 3 times the original function. And let's see what spills out. So notice that when I distribute the 3, these e to the 3x's pieces go away. So I'm left with 2 plus 6x plus 3, which equals 6x plus 5. So there you go. We know for sure that this thing is a solution because when we plug it in, we got truth. All right, so part of this first homework set, the stuff from 1.2, there are going to be a few where you're confirming that something is the solution, and this is all you're doing. You're going to take the respective derivatives, plug them in, and show that you actually get truth. Okay, so that's what it means to be a solution, and this is how we check it. But not all solutions are created equal. There are actually 2 different ways we classify solutions, and I think you're probably familiar with this by now. You can have what we call general solutions, but we can also have what we call particular solutions. All right, so the general solutions, all this means is that there are some unknown constants in there. And a good example is the one that I just did. There was a c there, right? It was c e to the minus 3x. And that c could have been anything. It didn't actually matter because it got canceled out, right? So that c could have been a 5 or minus 37 or 1.6 billion, or it doesn't really matter. Now, you're used to this though. Think about integration. When you integrated, when you were just finding an antiderivative, remember what we did? We always put on the plus c because we didn't know specifically which function it was. We were good within a constant, but we weren't entirely sure the exact value. Well, anytime you did that, anytime you put a plus c, that was a general solution. A particular solution, what happens there, and what we're talking about in that case, is that the c is determined. We know exactly what number that is. We know that it's a 4 or minus 12 or whatever. Okay, now go back to Calc 2 when you did those integrals and you got the plus c. Do you remember what we had to do to find the c? Remember what the situation was that led to being able to find the c?
To have an initial value, you remember?
We called it an initial value or an initial condition where we knew something about the function, right? And so to get particular, you need some information. So if you know a little bit of information about the function, you can go from the general to the particular solution. And we do call those initial value problems. So my phone just crapped out. It's coming back up. Hold on. All right, so I don't know where I lost you. So let's just back up. So initial value problems, IVPs, have two pieces. The first is the differential equation. Okay, so there's going to be a differential equation, kind of like what we saw here with the y prime plus 3y equals 6x plus 5. But then there's also going to be an initial condition. So let me alter this just slightly. So you can see what it would look like as an initial value problem. So we got this derivative. But then there would also be something like, let me say, comma, y of 0 equals 3. So now, not only do we know how the derivative relates to the function, but we know something about this function. We know that when you put 0 in, you get 3. So that y of 0 equals 3 is going to lead us to the particular solution in this case, right? So we already saw that the general solution was y equals c e to the minus 3x plus 2x plus 1, right? We just confirmed that. We didn't find it, but if we knew how to find it. All right, but now the y of 0 equals 3 tells us If we plug in 0 for x, we get 3 for y. So we're going to get 3 is equal to c e to the 0 plus 2 times 0 plus 1. Well, if we just simplify that a little bit, this tells us that 3 is equal to c plus 1, or c is equal to 2. So we went from well, it's something that looks like this, but I don't really know what c is, to, no, I know exactly what my function is. I can change that c into a 2, and so that's the function, the one and only function that satisfies this differential equation and passes through that point. Okay, so that's the difference between a general solution and a particular solution. The general solution will have c's. The particular solution, we now know what those values of c are because we know other things about the function. So you've seen this. You've totally seen this. You just haven't seen it maybe formalized. And you definitely haven't seen it where you might get more than one arbitrary constant. And that can definitely happen with differential equations. So let me give you a slightly more complicated problem. Slightly more complicated differential equation. But let's again talk about finding particular versus general. All right, so how about this one? Let's say our differential equation is y double prime minus 4y equals 0. Okay, so we're going to try to find a function whose second derivative, and when you take away 4 of the original function, ends up equaling 0. Okay, well, let me give you the general solution. And we're going to actually confirm it again. So let's confirm the general. And I'm just going to tell you that the general form for this is going to be y equals c1 times e to the 2t plus c2 e to the minus 2t. Okay, so check out what's a little bit different here. This now has 2 different arbitrary constants. And we are going to label them so that we know the difference, C1 and C2. This is a little bit different than what you're used to. You're used to finding 1C, back when you just integrated. And we even did those tricks where like, oh, we're going to take C, add some random number to it. We're still going to leave it as C and all, right? Well, now these are 2 different arbitrary constants. But I want to show you that this is still going to be the general solution. So let's get the second derivative. So y prime, that's going to be 2c1 e to the 2t minus 2c2 e to the minus 2t. And then if I differentiate one more time, I'm going to get 4c1 e to the 2t plus 4c2 e to the minus 2t. So if we plug those back into the differential equation, we're going to take the second derivative. So this thing that we just found. And we're going to subtract from that 4 of the original functions. Well, I think it's pretty easy to see that when I distribute that minus 4, I get things that just cancel out, and we do get 0. So for this one, yeah, the general solution has 2 C's, C1 and C2. So let's turn this into an initial value problem. right? So we already had this, that y double prime minus 4y equals 0. Let me tell you something about the function. And in fact, let's use the same that we had before. Let's say we know that y of 0 equals 3. I'm going to give you an initial condition. Well, if I plug that in to my general, I'm going to get 3 is equal to c1 times e to the 0 plus c2 times e to the 0, which tells me that c1 plus c2 equals 3. But do you see what the problem is here?
C1 and
Doesn't really narrow
C2 have
things down too
infinite
much.
solutions.
Yeah, like what are C1 and C2? I don't know. I just know they have to add up to 3. But as Jordan said, I mean, there's an infinite number of ways that that can happen, right? Maybe it's 1 and 2. Maybe it's -8 and 11. Maybe it's decimals, maybe it's fractions. I don't actually have enough information.
So depending on the order of the differential equation determines how much information you'll need.
Exactly. Yeah. If you look at what this, you notice that this was a second order differential equation. And there are actually two facts I kind of want to point out now. The order is going to tell you two things. One, it's going to tell you how many arbitrary constants you're going to have. So like the second order, we ended up having 2 arbitrary constants. First order only has 1. If it's a fourth order, they're going to be 4, and so on. Okay, so order is going to tell you how many arbitrary constants. And then that also tells you how much information you need to know. Because if there are 4 arbitrary constants, 4 variables, and I need to get the value of all 4, I need 4 equations with those 4 variables. Right? If I've got 2 unknowns, I need 2 equations for those 2 unknowns. By now, you guys with your linear algebra should be 100% on the, oh yeah, you need the same number of equations as your unknowns. So remember earlier I said order is a big deal because it tells you how to solve it. Not only does it tell you how to solve it, but it also tells you what to expect, which is good to know, right? It's really good to know, oh, this one should have 4 unknowns. If I don't have 4 unknowns, I did something wrong. Now, since you guys have already done linear algebra, I'm going to, this is a slight spoiler because it ties back to linear algebra. You remember when you talked about, oh, I don't know, say dimension of a space, right?
Yeah.
The dimension of a space, what did that tell you? Like if I told you there was a 3-dimensional space, what's that make you think?
Makes me think of 3x3 matrix.
Okay, so you think 3x3 matrix. How about in terms of, say, a basis? How many
3 vectors in the basis.
Yeah, so the dimension is how many linearly independent vectors are in that basis. Okay, well, the reason I'm bringing this up is when you solve differential equations, you're actually finding a solution space. Oh, and by the way, if anyone in here or watching these videos has not taken differential or linear algebra, and you're like, I have no idea what you're talking about, that's okay. Don't worry about it. It doesn't matter. I'm just trying to tie this to stuff from linear. What you're finding is a solution space. There's a basis to that space. The basis vectors are functions. Well, if you got a basis, you get the space by taking linear combinations of those functions. Hey, check it out. This is a linear combination of the functions e to the 2t and e to the minus 2t. E to the 2t and e to the minus 2t are a basis for the solution space of this differential equation. All right. And they're intimately tied together. So the fact that most of you have taken linear algebra is actually going to help a little bit with differential equations because you're going to start seeing why. All right, if it's an nth order, I'm going to have an nth dimensional space and I need to find n linear independent functions, and yada, 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 yada. All right, well, anyway, if we come back to this, right, that's not enough information. So what we would have seen if this was an initial value problem is not just say y of 0 equals 3, but we would have been told something else. And just for the hell of it, let's say we're told something about the derivative. The derivative at 0 equals 1. It could have been, we know that y of 2 equals 4 or something like that, but I'm just going to go y prime of 0 equals 1. Well, we can use that to get another equation with C1 and C2. So let's look at the derivative. Since we already found that along the way, we can go ahead and just bring that back in here. So the derivative is equal to 1 when when the t is 0. So we're going to get 2 c1 e to the 0 minus 2 c2 e to the 0. And now here it is. Here's our system of equations that we can use to find the values for C1 and C2. So we can take care of this one pretty quickly. If we just double this guy, we're going to get 6 is equal to 2C1 plus 2C2. So these C2s are going to cancel. We get C1, 7 is equal to 4C1, or C1 is 7/4. You can plug that in to find that C2 is equal to 5/4. So it required a little bit more information, but now we're able to find our particular solution. And so we know for this initial value problem, that solution is going to be y equals 7/4 e to the 2t plus 5/4 e to the minus 2t. It satisfies the differential equation and also satisfies the two initial conditions. All right, so clearly you can see that higher order is going to be more complicated because there's more stuff we're going to have to do when it comes time to finding particular solutions. And that is true. I'm not going to sugarcoat it. I'm not going to pretend that, you know, yeah, everything's no. The higher order, the higher the order, the more work we're going to have to do because it's a bigger space. It's going to have more solutions. It's going to have more unknowns. It's going to have more C's. All right. But there is good news. There is good news that as you go higher order, you use the same techniques as you use for the lower order. So at least we don't have to learn anything new. It's just going to lead to more work. That'll make more sense when we get there. All right. But that's the difference between a general solution and a particular solution. With the particular, we actually go and we find the values of C. All right, so how are we feeling so far? Good? Because I know what you're all dying for. You're all dying for I mean, yeah, this is great and all, but tell me how to find the general solution. Don't just tell me to check it. Well, that's what we're going to be doing over the course of the next months, is working on how do you find those general solutions? Because it depends. It depends on the structure, depends what we've got, and sometimes it's easier than others. But it's going to really come down to pattern recognition. Okay, so that's a little bit of what these are, what differential equations are, and what we're looking for when it comes to solutions. But the next thing I want to talk about real quick are ways to kind of visualize these, or to help us visualize these. And I want to talk about what we call slope fields. Now, the first thing that you should know for slope fields is that we use these for first order. Okay, we don't use these for higher order differential equations. We only use them for first order. Okay, but that should kind of make sense. Just think about the name, slope fields. And what is it about derivatives that tells you slope? Well, it's the first derivative. Okay, so slope fields are used for first order. You could do something similar, I guess, for second order if you called it a concavity field. I know that's a really weird kind of thought to have, but we could kind of do the same. But anyway, slope fields, we use these just for first order. All right, what they actually are is they're graphs. And they are graphs of the slopes at points in the plane. All right, so let me show you what I mean. Let's say we're looking at y prime plus y equals x. So here's a first order differential equation. Y prime equals, or sorry, y prime plus y equals x. So we're looking for a function whose derivative, when added to itself, gives you x. All right, so easy enough question. Right? But its solution, yeah, we're still not ready. But here's what we can do. We can actually use a slope field to help us get an idea of what that solution looks like. So here's what we're going to do. I'm going to put some tick marks on here. And we're literally going to calculate the slope at various points on the plane. To help us do that, I'm going to rewrite this as y prime equals x minus y. All right, so here's what we're going to do. Let's go to various places and calculate y prime. So for example, at the origin, at 0, 0, I plug 0 in for x and y, I get a derivative of 0. So think about what a slope would look like, or what a line would look like with a slope of 0. It's just going to be a little horizontal line. So I'm going to write a little horizontal line segment there. Draw a little horizontal line segment. So now let's move over to the point 1, 0. At 1, 0, if I plug that in, 1 minus 0 is 1, and I get a slope of 1. At 2, 0, I get a slope of 2. At 3, 0, I get a slope of 3. 4, 0, I get a slope of 4. So notice how those slopes are getting steeper as we move that direction. If I go the other direction, I'm going to get minus 1, minus 2, minus 3, minus 4. But obviously I can go to other places. So like if I went to 1, 1, I would get 0. If I went to 1, 2, I would get negative 1. If I went to 1 minus 1, I'd get a slope of 2. Right? And so I can continue doing this all over the place and get all kinds of different values for my slopes. Right? So I basically keep doing that, and it's going to create my slope field. I'm going to hop down to my computer, and we're actually going to, I'll share one. I'll show you what this looks like. But while I'm doing that, I stall for a little bit of time and talk. Does this look familiar? Do you remember doing something similar to this in a different class?
Yes.
Yeah, fourth quarter calc.
Okay, what did you guys do in fourth quarter calc that was like this?
Vector fields.
Yeah. So vector fields and slope fields are really the same thing. It's just now we're not drawing vectors. We're just drawing the little line segments.
I think we did something that was identical to this in one of Larry's classes, actually. Like we all had to go up on the board and mark an approximation of how the slope would look on, as a little line like that.
Okay, I wouldn't be surprised if that happened. I mean, it could have been second quarter
Yeah,
last year when you guys were looking at integrals.
I think that's what it was. It's hard to remember because it's kind of all the classes have kind of blurred together with quarantine and stuff. So
Yeah, but by this point, you're right. All right, well, hopefully I have about enough time. You guys can all see my slope field generator here. This is just one from Desmos. But you'll see if you look, it says let G be dy dx, and then we enter our G. So this one is actually drawing a graph of the slope field that's y prime equals 2x over y. For the one that we're doing, ours was y prime equals x minus y. And so here's a graph of that slope field. And if you look at it, you can actually see that what I drew on the board, you might be able to still see it in a small window there, but it's starting to form this, right? Like think about it, 0, 0, we had slope of 0. Then there was slope of 1, 2, 3, 4, it got steeper. And you can see some of the other lines that I did, it was flat here, had a slope of -1. But seeing Jacob mentioned how you guys did this with Larry, where he had to go up and kind of draw what it would look like. That's how we can use this to help us out. Like imagine I gave you an initial condition. And in fact, you know what I'm going to do? Let me do this. I'm going to steal this. Give me a second. Because I'm going to pull up something else here. Okay, so you should see something different now. You should see my paint window. Everybody see that?
Yeah.
Okay. So here I just copied that slope field so I can draw on it. Ignore that little bit, oops, on the bottom where you can see all of our names and everything. My screen, if you had any idea what my screen looked like, all the different things I have open as windows, you would just be floored. But anyway, that's what happens when I do a screenshot. But here's what I'm going to do. Let me go ahead and draw on this. And I think that probably is good enough. Let's see what it looks like. Okay. All right. So imagine I was going to try to draw a solution to this, a particular solution. All right. And let's say we were given that initial condition of y of 0 equals 3. We've done that a few times here. So we're going to be up here, y of 0 equals 3. So what I need is my line to have a slope of the tangent, or my curve to have a tangent slope of, looks like around -3. So it's going to come down in this direction. But as I come down in this direction, notice that I flatten out. And then once I get to the other side, I start going upward. And so this is roughly what the solution, the particular solution with y of 0 equaling 3 would look like. Let me go to a different starting value. Like, let's say we went with y of 4 equals 0, like I'm right here. Well, now I'm going to go up, but eventually I'm going to flatten out. And on this side, I'm going to go down, but get steeper. So there would be another solution. This is another particular solution, but because of a different starting point, right? This time I was starting there. So you can use slope fields to get an idea of what this shape is going to look like, or what these graphs are going to look like. And this was very much like what you did with vector fields, right? You use vector fields to figure out what direction things were going and they were heading. Well, slope fields are no different. We're just finding it in a different way, right? The slope field is just coming from the derivative, as opposed to the vector field coming from the vector. All right, so we're just going to use slope fields for what they are, a way to kind of visualize what's going on. But think of them as vector fields, and you're going to basically follow those arrows, and you're going to bend as you need to. And sometimes it can even show you things like equilibria, right? Remember, equilibrium means you're at a place where everything is just sort of even. And you may have noticed when I drew that graph, there was that point where it just sort of like all started coming to this one line. Well, that was an equilibrium state for our solutions. They're going to approach that line as we go towards infinity. And so that's another thing that we're going to talk about when we solve differential equations, is we're going to look at what are patterns as we go to infinity. Are there equilibrium values and things like that? And slope fields can definitely help you out. All right, well, I think this is a good place to stop for today. I know we still have a little bit of time, but I don't think you guys are going to complain. We're somewhere in the middle of 1.3, so we're actually ahead of schedule. Yeah, we'll see how long that lasts. We're slightly ahead of schedule, but you guys are totally equipped to do everything from 1.2. The homework from 1.2 you could all do and should be able to do in a pretty quick manner, because it's just a matter of, you know, finding particular solutions given initial values, confirming that things are solutions to differential equation, classifying by order, right? Things like that. So it should be pretty quick. So my recommendation is get in there, work on that. If you would like to turn that in before Monday, I would not be upset by that. That way I don't have a ton of stuff that's all given to me at the same time. But of course, that's totally up to you. All right. Anyway, so what we'll do next time is we'll start getting into the, how do we solve these guys, right? Might as well just dive right in, all right? So with that, I'm going to wish you all a very wonderful couple of days, and I will see everybody on Wednesday.